Hey kids! Alright, just before we get into the next lesson, I actually had a little thing I wanted to show you. I mentioned in the last video where we introduced logs in a mathematical way, I mentioned that logs have a lot of uses, and it wasn't always obvious what the uses are, but they're there. So I'd like to start this video off with just a little psychological experiment here. There's four squares with a bunch of dots. On the left, you can see there's two squares that are sparsely populated with dots, and on the right, you can see there's two squares that are heavily populated with dots. What I want you to do is just take a sec and determine, is there a difference in the number of dots between the two squares in the left column, and then I want you to determine, is there a difference in the number of dots between the two squares in the right column? And don't count the dots, just look at it and see what you think, okay? So I'm guessing if you actually did this, you can obviously tell that there's quite a difference in dots between the two squares in the left column. Now, is there a difference in dots between the two squares in the right column? If you look at it at first glance, I personally, okay, if I'm staring at them, looking up and down, looking up and down, they actually look like the same, but if I look real hard, I can find the odd dot that is in the bottom right square that is not in the top right square. But at first glance, they almost looked identical, and I had a hard time telling the difference. This is a really important fundamental property with how we perceive things. When there's a little bit of something, we can notice a change very easily. When there's a lot of something, we have a hard time noticing the change. For example, in the top left, I only have 10 dots, and in the bottom, I actually have 20. In the top here, can you tell what the difference is? It's not easy. I'll show you what the difference is, or the actual amount of dots. These are the number of dots in each square. So it was really easy to tell the difference between the 10 and the 20. 110, 120, much, much harder. So what this means for us, and how this connects to logarithms, is that perception is logarithmic. So when you are looking at something, the difference between 10 and 20 versus 110 and 120, that can be explained with logarithms. So what I'm going to do here is I'm going to just show you a little something. This is an excerpt from Wikipedia here. It's called the Weber-Fechner Law, and there's the little graphic that I stole. And you can read the whole thing if you're very curious. It's actually quite interesting. You might need to know a tiny bit of calculus to really get the math, but you don't need to know any math to get what it's saying. And it's this part right here. The relationship between stimulus and perception is logarithmic. The logarithmic relationship of, okay, and it talks about geometric progressions. The big thing I want to mention here is this statement here. It gets a little bit technical, but what this says is if the stimulus is tripled in strength, like you multiply it by making it stronger and stronger, the corresponding perception, what your brain thinks, will be like adding it together. And what this means in terms of something very fundamental that you can understand is light, for example. And I've noticed this. Some light fixtures will have 3 or 4 or 5 light bulbs in it, and one of them will burn out. And what's very interesting about it, you can try this if you want. You don't have to burn out your light bulbs, so you can unscrew them. You can actually see that if you've got one light bulb working, the room will seem kind of bright. And if you put 2 light bulbs in, so you multiply the amount of light by 2, it will seem brighter, but it actually won't seem twice as bright. And if you put in 3 light bulbs or 4 light bulbs, every time you add a new light bulb, you're increasing the amount of light, but it's not going to seem like it's 1, 2, 3, 4 times brighter. It's actually going to kind of level off. And the difference between 3 and 4 light bulbs is actually very little. Go ahead and try it. Go find a bathroom light fixture if you have one of those styles, and do it. Go and unscrew one and see what happens, and keep unscrewing, and you'll notice when you're down to 1 or 2 lights, there will be a real big difference every time you get rid of one. On a graph, how this connects with logarithms is, well, here's the logarithm graph. So what I did is I just plotted log x, and I plotted, so there's no labels here, what the bottom x-axis will be is the number of dots. So I'm referring back to the dot thing, but this could be anything. It could be the number of light bulbs, or the number of decibels of sound, or anything that you can measure intensity with. So in this case, it's dots. What the y-axis is the perception of how many dots there are, or how bright, or how loud it is. So the y-axis is the perception. So if we're saying perception is logarithmic, then when I have 10 dots, we'll say there's a perception of 1. Don't worry about the scaling. But if you have 20 dots, it might be a perception of 1.3. So doubling the amount of dots gives us a 30% increase in perception. But when you get all the way up to 110, you're at 2.04 for perception, and 120 would be 2.079. The difference is tiny, and if you want to see the difference here, I made some horizontal lines. The difference between 10 and 20, so the vertical distance in between the two would be like the difference in perception, and that's noticeable. But if you want to go between 110 and 120, you can see the vertical distance between those two lines is barely noticeable, because perception is logarithmic, and as I increase more and more and more dots, it starts to get harder and harder and harder because of the shape of this graph to determine the difference. And this is for everything. Your eyes work this way. When you double the amount of light, you don't double the perception. One more interesting thing I'd like to point out, and you can even see it up here in my beautiful newly shaven bald head, you can see the light around me. It looks almost like a halo. It's not that bright when you look at it, though. When I look at this, I turn my head around, I go, I can see out the window no problem, but the camera is absolutely saturated. And the reason for this is very simple. My eyes, when I look outside, the sunlight is very bright. It's actually overcast right now, but the sunlight is super bright, and my eyes tone it down because they're logarithmic, just like the rest of my body. So it doesn't appear very bright. Even though the intensity might be up at like 110 or whatever, it doesn't appear bright because of the logarithmic nature of my eyes. The webcam, however, doesn't see light the same way my eyes do. I'm just going to get rid of, I'm not going to get rid of this, but what I'm going to do is I'm going to add one more line. The webcam, I don't necessarily know if it's exactly like this, but I'm going to go ahead and just sort of say it's something more like a linear relationship, where if you double the amount of light for the computer's webcam, it will actually double the brightness on the screen. So it's more of a linear relationship. So that if I'm all the way down here at 100 watts of light or whatever you're measuring it in, it's going to seem very not so bright to my eyes, but to a webcam, it's going to look super bright. And that's why it's getting saturated. And the same thing goes with the reason you can't hardly see my face. I almost look like a silhouette. When the brightness goes down, when it gets quite low, I go from, let's say, 110 brightness down to 10. Well, if this is logarithmic on a base 10 scale, and it might not be base 10, I'm just sort of spitballing here, but the brightness in my eyes will go from 2 to 1. It'll appear half as bright. But the difference from the webcam way up here at 100, wherever that is, it will give me a relative perceived brightness of like 20, and if I tone the amount of light coming down to 10, now its perceived brightness is 2. So on a camera, which is linear, the change in brightness of the light actually shows up as a tenfold difference, which is why my face looks so dark and why the backlighting is so bright, but your eyes are much better. And that's a fact of evolution there, right? Because sunlight is very, very intense, and our eyes needed a way to kind of deal with that. Same with sound. Loud sounds are actually insanely loud, but our ears tamp it down with the logarithmic detection of sound. Anyway, I hope that was interesting. I find it personally very interesting, and it explains a lot of times where when you're out at night and you see a beautiful sky full of stars and you think, wow, I'd love to take a picture of it. Then you take a picture with your phone and you can barely see the stars. It's because there's barely any light and your phone just isn't logarithmic. Now there's someone out there going, well, I thought the new iPhone could take pictures of stars. Actually, I think the Google Pixel was claiming that. They obviously have some software that's starting to make the camera more logarithmic so it matches our eyes. So anyway, that's what technology can do, and people are working on that. But the old-fashioned stuff, especially the old film photography, totally linear and totally not the same as our eyes. Anyway, thanks for watching. We're going to put, I guess, part 2 in with the actual lesson on transforming graphs in just a sec here. But let's stop it there. Bye for now.